This video provides an overview of the Intersection Lifecycle Cost Analysis tool developed for NCDOT. This tool will provide an estimate of the expected long-term benefits and cost associated with converting two-way stop-controlled intersections to one of three alternative configurations. The possible intersection configurations under consideration in this particular tool are always stop control, roundabouts, and signalized intersections. You will notice this tool is based on a Microsoft Excel application. Shown on the bottom are 7 tabs that should be completed in the order provided. On each sheet you will also notice that there are color-coded areas. These are described in points 1 through 4 on the bottom of this sheet. Yellow is used to represent areas you need to provide data or other inputs. Orange is always shown in a button form that can reset or view defaults as shown in step 1, or in the following steps can be used to go back to a previous step. Green is utilized in a button form that allows the user to proceed to the next step or to run an analysis, and blue cells do not need to be changed. Let's talk about some of the inputs that will be needed on this page. First, you'll need to put the major and minor approach. I'm considering Forestville Road at Burlington Mill Road, which is located in Wake County. My name is Chris Cunningham. I'll next need to assume or provide the major approach orientation, which is very important for analysis. In this case, Forestville Road is my major approach and it has a north-south orientation. I've also entered the analysis date for record-keeping purposes, and then I will need to enter the operational analysis period. This will need to be between 10 and 25 years. Another very important consideration is whether or not the two-way stop-controlled configuration that's being replaced is one-stage or two-stage. A one-stage crossing movement crossing the major approach in a single stage without a median. In other words, they're crossing both directions of traffic on the major approach. A two-stage configuration would describe a median where you could stop before crossing the conflicting approach on the other side of the major road. In this case, I have a one-stage crossing. This is a high growth area, so I've entered 6%, with low heavy vehicles, which I've entered 2%. You'll also need the peak hour factor and the area type. And for area type, we have 3 area types you can consider: urban, suburban, and rural, and this is a suburban location. You'll then need to enter the fuel cost for unleaded fuel and diesel, and then proceed to step 2. In step 2, the traffic flow demand data, there are 3 options for entering traffic flow data. The first option is AADT, the second option is counts during the peak period, and the third option is a direct input from turning movement counts. Let's start with the AADT for different movements. Shown here, you'll need to enter the flow rate data for 2 directional ADTs for the east, west, north, and southbound approaches. You'll see I've already entered some data for those 4 approaches. Secondly, you'll need to enter the traffic turning distributions for the left, through, and right turns for east, west, and north and southbound traffic. See here that I've already entered turning movement distributions for each of those approaches. Distribution. And using the blue button. If we click the blue button, you'll notice there are 5 options for entering data. First, you can enter 2 equivalent peaks for a minor AM and minor PM, or you could do one of the other 4 options, such as a minor AM, major PM, 2 peaks major for AM and PM. You may have a noon peak, which is the 4th option, or you may be in a coastal environment or an environment with no prominent peaks. In our case, we have a minor AM and PM peak, so I'll choose that. Note that the percentages automatically update. It's important that you understand that the default hourly factors are built based on sites that were already converted from two-way stop control to always stop controlled intersections, which makes it very useful for inputs. Another option for entering traffic flow demand data is to use direct counts from the peak period. Notice that several of the entries are the same as the AADT entries. For instance, the current traffic turning distributions will need to be input, and those have carried over from the ADT entries that we entered earlier. In addition, you'll need to enter the hourly demand default distributions by clicking either the blue button or direct input, and notice that those have also carried over. Two differences are shown at the top. First, you'll need to do approach volumes for the east, west, and north and southbound approaches. Notice I've entered 4 approach volumes already. You'll also need to tell the peak period that's being considered. A third option for entering traffic flow demand data is to enter counts directly from a turning movement count. Notice here I have 24 individual hours for each of the 4 approaches that I can enter data. Many turning movement counts are not done for 24-hour periods, but instead might be taken during 16-hour or 18-hour increments. For hours where data is not collected for a turning movement count, you will still need to do a hard entry of 0 to make sure that it populates the data correctly. Notice that the bottom entry is repeated from the first 2 options, ADT and peak period, where you're required to enter left, through, and right percentages for each of the 4 approaches. Note that this is carried over from my original entry into ADT for different movements option. You can then proceed to step 3, but make sure that you have the correct entry that you would like to use. In our case, we have chosen ADTs for different movements. We'll now proceed to step 3. In step 3, you're asked to enter historic intersection crash data. We recommend a minimum of 3 years of data, but no more than 5. You'll be asked to enter the data by severity type K through O. These are defined below the table, with K being a fatal collision and O being property damage only. Notice here I've already entered data for K through O for the first 3 years prior to the intersection being converted from a 2-way stop control to one of the other 3 configurations. If you only have 3 or 4 years of data, you'll need to leave the other years blank in this case to make sure that the averages stay consistent on the bottom. You'll then proceed to step 4. In steps 4 through 6, we are asked to enter design and construction costs along with the geometric configurations for roundabouts, always stop controlled intersections, and signalized intersections. We'll start with the roundabout configuration in step 4. First, we are asked to enter the initial cost estimation. Note here we've entered $750,000 based on one of 3 ranges that are provided below. Notice that the ranges go from about $500,000 to $1 million, and we've given basic descriptions of what those options cover based on data from NCDOT on roundabout configurations in recent years. In our case, as we said, we assume $750,000 because we do have some purchases that will take to the geometric entries. Notice that we're asked to enter right turn bypass configurations for east, west, north, and southbound legs. For the east, west, and northbound legs, we've assumed a standard yielded entry for the single lane roundabout. However, for the southbound north leg, we've assumed an add lane or a slip lane because the traffic volumes in step 2, traffic demand, were high for the southbound approach right turns, which were 20% of 10,000 two-directional ADTs. Before moving to step 5, always stop controlled configurations, you should note that the roundabout configuration is only considering single lane roundabout analysis. Dual lane roundabouts cannot be analyzed in this program. We will now move to step 5. Notice here that step 5, the design and construction costs along with the geometric configurations are very similar to that in step 4, the roundabout. Again, we are provided default options with a low of about $10,000 up to a high option for always stop control of $75,000, along with the description of what those types of costs are based on conversions from NCDOT over the last few years. In our case, we're looking at an average option with the addition of flashers. So we will assume $25,000 is our initial cost estimation if we wanted to look at an always stop control configuration. Next, we are asked to enter the lane configuration from a geometric standpoint. Notice here that the defaults are set to for lane 1 in eastbound, west, northbound, and southbound directions. This describes a shared left through and right turn lane at each of the approaches. If you would like to have a dedicated left turn lane on any of the approaches, you would need to enter that as a lane 2 turned on. For instance, our southbound approach had a heavy volume. We may assume to put a dedicated left turn on that particular lane to separate the lefts from the shared through and rights. So in this case, the southbound approach would have a dedicated left turn lane in lane 1, and lane 2 would be a shared through and right turn lane. We will now proceed to step 6. In step 6, we're asked to enter similar information for signals. Notice here we are asked to enter an initial cost estimation, and again we're given default values based on recent configurations by NCDOT. In our case, we're going to consider a low option because this is a standard installation with minor geometric changes and utility changes. So we'll assume approximately $60,000. Next, we're asked to enter lane configuration data. It's very important to understand what the entries need to be in this case. We'll use the drawing here on the right to explain how to enter left, through, and right entries. Through lane configuration, right turn lane. Left and the through share, and there is no dedicated left turn with the left. 0, 1, 1. The upper right hand, we have dedicated lanes for the left, through, and right. So entry would be a 0, 1, 0. The through, we would enter a 1 for the left turn, a 1 for the through, and a 0 with the through. Therefore, the entry would be 0. There's a dedicated left turn lane, and the south. We're in a suburban area with 2 to 3 phase signals. We'll assume a minimum cycle length of about 60 seconds and no more than 120 seconds. The lost time per phase will be 4 seconds. One important thing to note is that you must click Run Analysis on step 6. Watch what happens if I go to the summary output without clicking Run Analysis. I will get a Microsoft Excel pop-up box that will remind me to make sure that I press the Run Analysis button in step 6 to make sure the results are updated. Let's go back to step 6 in this case and hit Run Analysis. Depending on the speed of your computer, this could take a couple minutes. For my computer, it took about 46 seconds. You can now proceed to the summary output, which automatically takes place after running the analysis. The summary output page is broken into 2 sections. First is a snapshot of the intersection options in the first year of analysis only. As noted in the bottom of the table, this table is not the final output of the tool analysis and should not be used to compare the long-term cost of two-way stop control to other alternatives. Last, and probably the most important piece of this page, is the long-term difference between two-way stop control intersections and each of the three conversion alternatives. We'll cover those shortly. Back up to the snapshot of intersection options in the first year of analysis. Provide the percent reduction when looking at fatal and will reduce 7 conversions, about 40. Actually look at the year of analysis section you would expect. Roundabout, you would expect 2 points that year, and signal 4 are summarized in annual. Next are the numbers for delay in the first year. Notice that the user delay is provided for each of the 4 alternatives, 3 of them being alternatives for conversions from two-way stop control, the roundabout, all-way stop, and signal. These again are annualized in a user delay cost for comparison purposes during the first year. Last, the user fuel costs for the first year are provided for each of the 4 alternatives to compare what the fuel estimates would be, along with construction cost and the annual maintenance cost. Again, this table only provides data for the first year and should not be used for direct comparison purposes. It's merely a snapshot. In the second table of the summary output page, you'll notice the long-term difference between two-way stop controlled and conversion alternatives. At the bottom in yellow, you'll notice the total long-term benefits, or the net present value, is calculated. This is the life cycle cost analysis that is being completed. The alternative with the highest net present value is the best alternative considering all of the options over a long term, considering delay, safety, fuel cost, and maintenance, along with design and construction. Then the benefits, which from conversion from two-way stop to one of these 3 alternatives, and the user fuel cost savings. So the benefits are calculated as the sum of these 3 items. The costs are calculated as a conversion for construction cost, regular maintenance cost, and then service life replacement. For a roundabout, this is 0 because the service life is considered to be 25 years. The net present value is the sum of the benefits, or the first 3 values, minus the sum of the cost. Again, the number with the highest value is the best choice from a life cycle cost analysis standpoint. In this case, the always stop controlled intersection would be the best conversion type.